In 2011, Adam Rees won the Nobel Prize in Physics. He won it for one of the most consequential discoveries in the history of science. The finding, made in 1998, that the universe is not merely expanding, but accelerating. That something is pushing the cosmos apart faster and faster with every passing moment. A force so mysterious and so poorly understood that scientists simply named it dark energy and acknowledged that they had no idea what it actually was. The Nobel Prize was the scientific community's formal recognition that Rees and his colleagues had permanently changed our understanding of what the universe is and where it is going. Adam Rees is not a person who makes alarming statements casually. He is a careful, rigorous, deeply technical cosmologist who has spent more than 2 decades making the most precise measurements of the universe's expansion in human history. He is not given to hyperbole. He is not a sensationalist. And recently, Adam Rees said something that should make you stop and pay attention. He said we may have misunderstood the universe. Not in the modest, incremental way that science is always refining its models. Not, we got the decimal place wrong, or the uncertainty range was slightly too narrow. He said the discrepancy at the heart of modern cosmology, the gap between 2 different measurements of the universe's expansion rate, is large enough, robust enough, and resistant enough to every proposed explanation that it may require entirely new physics. Physics that is not in any of our current models. Physics that no one has yet written down correctly. The discrepancy has a name: the Hubble tension. And it goes like this. There are 2 ways to measure how fast the universe is expanding, what astronomers call the Hubble constant, the number that describes the rate at which galaxies are receding from us per unit of distance. One way looks at the nearby universe, measuring the distances to galaxies and comparing them to how fast those galaxies are moving away from us. This method, the cosmic distance ladder, built from Cepheid variable stars and Type 1a supernovae, gives an answer of approximately 73 kilometers per second per megaparsec. The other way looks at the early universe using the pattern of temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, to infer what the expansion rate should be today, given everything we know about how the universe has evolved. That method gives approximately 67, 73 versus 67, a difference of about 8%. In a field where measurements are supposed to be accurate to better than 1%, that is an enormous gap. For years, the most hopeful interpretation was that one of the measurements was wrong, that there was some subtle systematic error, some uncorrected bias in how the distance ladder was calibrated, some impurity in the CMB analysis, some overlooked effect that inflated one number and suppressed the other. If the measurements were just a bit off, the tension would dissolve, the models would agree, and the universe would make sense again. The James Webb Space Telescope was supposed to settle it. Webb was the instrument that could look at Cepheid, variable stars, with unprecedented precision, in infrared wavelengths that cut through the dust that complicates visible light observations, with a resolution and sensitivity that no previous telescope could approach. If there was a systematic error in the distance ladder, Webb would find it. Webb did not find it. What Webb found instead was that the distance measurements were correct, that the Cepheids were correctly identified, correctly measured, correctly calibrated, that the tension between 67 and 73 was real. And not only that, Webb found other things in the early universe that do not fit the models either. Galaxies that are too large, too bright, too organized, and too numerous to have formed as quickly as the standard model of cosmology says they should have. A class of strange objects, the little red dots, that initially looked like massive early galaxies, but turned out to be something even more puzzling. An early universe that is in multiple independent ways, not behaving the way our best physics predicts it should. This is the story of what Webb found, what Ries and his colleagues are warning about, what the rival teams are fighting over, and what it might mean if the universe turns out to be fundamentally different from the one we thought we understood. Chapter 1: The Measurement That Won a Nobel Prize, and why it's now a problem. To understand the Hubble tension, you need to understand what the Hubble constant actually is and why measuring it matters so deeply. In 1929, Edwin Hubble published a finding that permanently altered humanity's understanding of its place in the cosmos. Looking at the spectra of distant galaxies, Hubble noticed that almost all of them showed a redshift. Their light was stretched toward longer wavelengths, indicating that they were moving away from us. More importantly, the more distant a galaxy was, the faster it was receding. This was not galaxies moving through space in random directions. This was space itself expanding, the fabric of the cosmos stretching, carrying the galaxies along with it like dots painted on a balloon being inflated. The rate of this expansion, how fast galaxies recede per unit of distance, is the Hubble constant, h0. A galaxy 1 megaparsec away, about 3.26 million light years, recedes at h0 kilometers per second. A galaxy 2 megaparsecs away recedes at 2h0. A galaxy 10 megaparsecs away recedes at 10h0. The constant tells you how the universe is stretching right now, at this moment in cosmic history. Measuring h0 requires measuring two things for each distant galaxy: how fast it is receding and how far away it is. The recession velocity is easy. It comes directly from the redshift of the galaxy's spectrum, and redshifts can be measured with high precision. The distance is hard, very hard, extraordinarily hard in ways that have occupied the careers of hundreds of astronomers across more than a century. The difficulty is that there is no cosmic ruler, no way to look at a distant galaxy and simply read off its distance. Distance must be inferred indirectly, using objects whose intrinsic brightness is known, so-called standard candles. If you know how bright something actually is, and you can measure how bright it appears, the difference tells you how far away it is. The same principle that lets you judge the distance to a streetlight. You know roughly how bright streetlights are, so if this one appears dim, it must be far away. The cosmic distance ladder is a sequence of overlapping standard candle techniques, each one extending the reach of the previous one, that allows astronomers to measure distances from the solar neighborhood to the cosmological scales where the Hubble constant measurement is meaningful. The first rung is geometric parallax, the tiny apparent shift in a star's position as Earth moves around the Sun, which gives a direct trigonometric distance measurement. The second rung uses Cepheid variable stars, stars that pulsate with a period directly related to their intrinsic luminosity, making them reliable standard candles out to tens of millions of light-years. The third rung uses Type 1a supernovae, the explosions of white dwarf stars in binary systems, which reach a consistent peak luminosity that makes them visible across billions of light-years. This is the method Adam Rees and his colleagues have used for decades to measure the Hubble constant. And their answer, consistently, across multiple iterations of the measurement with progressively better data, has been approximately 73 kilometers per second per megaparsec. Now contrast that with the completely independent method. The cosmic microwave background is the thermal radiation left over from the early universe. The afterglow of the Big Bang, emitted approximately 380,000 years after the universe was born, when it cooled enough for hydrogen atoms to form, and the previously opaque plasma became transparent to photons. The CMB fills the sky uniformly, coming from every direction at a temperature of approximately 2.725 Kelvin. It is the most precisely measured blackbody radiation in the history of physics. But the CMB is not perfectly uniform. There are tiny temperature variations, fluctuations of about 1 part in 100,000, that encode the density variations of the early universe. These fluctuations have been mapped with extraordinary precision by satellites including COBE, WMAP, and most recently, Planck. The pattern of these fluctuations, specifically the angular scale of the most prominent fluctuations, called the acoustic peaks, carries information about the early universe's composition, geometry, and dynamics. Using the standard lambda-CDM cosmological model, the model that describes the universe as composed of ordinary matter, about 5%, dark matter, about 27%, and dark energy, about 68%, the Planck collaboration has inferred from the CMB what the Hubble constant should be today, given how the universe has evolved over 13.8 billion years. Their answer: approximately 67.4 kilometers per second per megaparsec, 67.4 versus 73. The gap is not enormous in absolute terms. It is a difference of about 8%. But in the context of precision cosmology, where both measurements claim accuracy to about 1%, the discrepancy is enormous. If both measurements are correct, the two most precise ways of measuring the universe's expansion rate disagree by approximately 5 standard deviations. 5 sigma. In physics, a 5 sigma discrepancy is the threshold for calling something a discovery. A 5 sigma discrepancy between two measurements of the same fundamental quantity is not noise. It is a signal. Adam Rees, who has produced some of the highest precision distance ladder measurements in the history of the field, has been at the center of this debate since the tension first became apparent around 2019. And his position has evolved from cautious concern to something more pointed. In various interviews, papers, and public statements, he has increasingly used language that would have been unusual coming from him a decade ago. Language suggesting that the discrepancy may not be an error, but a genuine signal of physics that the standard model does not contain. When the Nobel laureate who won his prize for measuring the universe's expansion says we may have misunderstood it, the appropriate response is to take that very seriously. Not because authority settles scientific questions, it does not, but because Rees has more first-hand experience with these measurements than almost anyone alive, and his assessment that systematic errors have been exhausted is based on decades of direct engagement with every proposed source of bias. The measurement is right. The tension is real. And now the question is, what does it mean? Chapter 2. The SH0ES team versus the CMB, a decade-long fight. The Hubble tension did not appear suddenly. It emerged gradually as the precision of measurements on both sides of the discrepancy improved, and the debate about whether it was real or a systematic artifact consumed enormous quantities of scientific effort and produced a literature that runs into hundreds of papers. The battle lines formed between two communities with fundamentally different methodologies and different sources of potential error. On one side, the SH0ES team, supernova H0 for the equation of state of dark energy, led by Adam Rees and collaborators including Wendy Friedman, Alexei Filipenko, and others. This collaboration has been the primary driver of distance ladder H0 measurements for more than 2 decades. Their approach uses Cepheid variable stars in nearby galaxies as the middle rung of the ladder, calibrated against geometric parallax distances to nearby Cepheids, and extended to cosmological scales using Type 1a supernovae. On the other side, the CMB community, centered primarily around the Planck satellite collaboration, but also including the teams that analyzed the WMAP satellite data before it. These researchers extracted the Hubble constant from the CMB by fitting the entire lambda CDM model simultaneously to all the observed features of the CMB temperature and polarization power spectra. Their methodology is completely different from the distance ladder. No Cepheids, no supernovae, no direct distance measurements, but instead a precise measurement of the early universe's physics from which the present-day expansion rate is inferred. The critics of the SH0ES measurement have pointed to several potential sources of systematic error in the distance ladder. The most commonly cited is what is called crowding or blending, the possibility that in distant galaxies, the Cepheid variables measured by Hubble Space Telescope are not truly isolated, but are blended with the light of nearby stars that cannot be individually resolved. If the measured brightness of a Cepheid is contaminated by the light of nearby stars, the apparent brightness will be higher than the true brightness, making the Cepheid appear closer than it is, and inflating the inferred H0. The crowding correction has been applied in all the major distance ladder measurements, but critics argued that the correction might be incomplete. They also pointed to potential issues with the calibration of the Cepheid period luminosity relationship in the presence of dust, the interstellar grains that absorb and redden the light of distant stars. Dust reddening changes both the apparent brightness and the apparent color of Cepheids in ways that can be corrected using infrared observations, but the corrections are imperfect and could introduce systematic errors. Different dust extinction laws, different assumed infrared properties of Cepheids in different host environments, different metallicity corrections for the relationship between a Cepheid's chemical composition and its pulsation behavior. All of these were proposed as potential sources of bias that might be inflating the distance ladder H0. The CMB community, for their part, was not immune to criticism. Their extraction of H0 depends on the entire lambda CDM model being correct. If the universe contains some component, some form of early dark energy, some exotic light particle species, some modification to the standard picture of the early universe, that is not in lambda CDM, then the CMB analysis would infer the wrong H0. The CMB inferred H0 is not a direct measurement, but a model-dependent inference, and the model may be incomplete. This debate ran for years through the 2000s and into the 2020s. Papers were published arguing that crowding effects could explain some or all of the tension. Other papers showed that the tension persisted after applying more careful crowding corrections. Papers argued that the Cepheid period luminosity calibration was uncertain. Other papers calibrated it more carefully and found the same answer. Papers proposed new physics solutions to the CMB side of the problem. Other papers showed those solutions created new inconsistencies elsewhere. The scientific community needed a decisive measurement that could test the most specific systematic error hypotheses. The James Webb Space Telescope was that measurement. Chapter 3, Webb steps in, and the tension gets worse. The James Webb Space Telescope launched on Christmas Day 2021, deployed its golden mirror to its full diameter, cooled to its operating temperature at the second Earth-Sun Lagrange point, and began transmitting data in the summer of 2022. Its infrared sensitivity, its angular resolution, and its freedom from the distortions of Earth's atmosphere made it the most powerful tool ever deployed for measuring the cosmos. For Adam Rees and the SH0ES team, Webb was specifically the instrument needed to test the crowding hypothesis, the most persistent and most plausible source of systematic error in the Cepheid-based distance ladder. In 2023, Rees and his team published the results of Webb observations of Cepheid variable stars in several of the galaxies that anchor the distance ladder, the same galaxies that had been observed with Hubble for decades, whose Cepheids had been the foundation of the distance ladder measurements. The Webb observations were taken in near-infrared wavelengths, where the telescope's angular resolution exceeds Hubble's, where dust absorption is reduced, and where the contamination from stellar crowding would be most apparent if present. The team examined the Cepheids in 5 distance ladder calibration galaxies: NGC 4258, NGC 1559, NGC 5584, NGC 3447, and the Large Magellanic Cloud. For each galaxy, they measured the Cepheid brightnesses in Webb's infrared bands and compared the results to the Hubble-based measurements that had been the basis of the H0 equals 73 result. The conclusion was stark. The Webb measurements agreed with the Hubble measurements to within the stated uncertainties. The Cepheids were not being systematically blended with unresolved companions. The crowding corrections that had been applied to the Hubble data were accurate. The dust corrections were not systematically off. Every specific systematic error that had been proposed to explain the tension, tested against the Webb data, was ruled out. The H0 value derived from the Webb observations was 73.0, plus or minus 1.0 kilometers per second per megaparsec. Rees and his colleagues were explicit about what this meant. The systematic errors proposed by critics of the distance ladder method are excluded to high confidence. The tension did not go away. It got sharper. Before Webb, there was always the possibility, the hope, really, that the tension was a measurement artifact, that more precise observations would dissolve. After Webb, that possibility was closed off. the distance ladder measurement is correct. The tension with the CMB is real. And now, the universe owes us an explanation. In the media coverage of this result, Rees was quoted using language that was careful but unmistakable in its implications. The measurement, he said, was pointing toward something exotic in the universe's physics. Perhaps a new kind of dark energy that behaves differently at different cosmic epochs. Perhaps a new species of particle that was present in the early universe and changed the conditions from which the CMB emerged. Perhaps something else entirely, some ingredient the models are missing, that when found, will resolve not just the Hubble tension, but several other anomalies in modern cosmology simultaneously. The phrase something exotic is not casual language from a Nobel Prize winner. It is an invitation to the theoretical community, to the observational community, to everyone who has been watching this debate, to seriously consider that the standard model of cosmology, which has been one of the most successful theoretical frameworks in the history of science, is missing something fundamental. But Webb was not done delivering surprises. Even as the Hubble tension results were being absorbed, the telescope was producing a completely independent category of disturbing findings. Findings from the very early universe that compounded the picture of a cosmos that is not behaving as expected. Chapter 4. The Impossible. Early galaxies. Too big, too soon. When cosmologists say something is impossible, they do not mean it violates the laws of physics in the way that a perpetual motion machine does. They mean it is incompatible with the best current model of how the universe works, a model called lambda CDM that has been calibrated against decades of observations and makes specific quantitative predictions about how the universe evolved. Lambda CDM predicts that galaxies did not spring fully formed into existence. They built up gradually, hierarchically, through a process of small structures merging into larger ones over billions of years. The first stars formed in the first few 100 million years after the Big Bang, in small, dense clouds of hydrogen and helium. Those first stars formed small proto-galaxies. Small proto-galaxies merged over millions and billions of years into progressively larger structures. The large, massive, well-organized galaxies we see in the present-day universe, the Milky Way and Andromeda, and their hundreds of billions of stars, are the products of a very long assembly process. Lambda CDM makes specific predictions about what early galaxies should look like. They should be small. They should be irregular and clumpy, still in the process of assembling themselves. They should not be very massive. There simply has not been enough time in the first billion years of the universe to assemble the stellar mass of a large present-day galaxy. And they should be relatively few in number at the highest redshifts, because the largest, most massive structures take the longest to build. Webb found galaxies that appear to violate every one of these predictions. In the first year of Webb's observations of the early universe, specifically in the data from the CAUEERS survey, Cosmic Evolution Early Release Science, and the JADES survey, JWST Advanced Deep Extragalactic Survey, astronomers identified a population of bright, compact sources at extremely high redshifts. The redshifts of these objects, inferred initially from their photometric colors and later confirmed spectroscopically for many of them, placed them at times when the universe was less than 700 million years old. Some were at redshifts above 10, corresponding to less than 500 million years after the Big Bang. A handful were at redshifts above 13 and 14, corresponding to less than 300 million years, less than 2% of the current age of the universe. These objects were not faint wisps at the edge of detection. They were bright enough to be clearly detected by Webb, which means they were intrinsically very luminous. And luminosity, in the context of star-forming galaxies, is a proxy for the rate at which stars are being formed, or for the total mass of stars already formed. When astronomers converted the observed brightnesses into stellar mass estimates, they found objects that appeared to contain billions to tens of billions of solar masses of stars at redshifts where the standard model says only millions should be possible. One of the most discussed early examples was a set of galaxy candidates reported by Laba and colleagues in 2023, photometrically identified in early Webb data and estimated to have stellar masses of up to approximately 100 billion solar masses, comparable to the present-day Milky Way, at redshifts around 7 to 10. If correct, these masses would exceed the predictions of lambda CDM by factors of 10 to 100 at those cosmic epochs. The scientific community's immediate response was cautious. Photometric redshift and mass estimates carry real uncertainties. The conversion from observed brightness to stellar mass depends on assumptions about the stellar populations: how old the stars are, what their distribution of masses is, how much dust is present. These assumptions can significantly affect the derived mass. Perhaps the objects were misidentified, lower redshift galaxies with unusual spectral energy distributions masquerading as high redshift objects. Perhaps the mass estimates were systematically inflated by incorrect assumptions about the stellar populations. Spectroscopic follow-up observations that measure the actual spectrum of each object, allowing direct confirmation of the redshift and a more detailed characterization of the stellar populations, were urgently needed. And over the following 2 years, that spectroscopic confirmation arrived for many of the most extreme candidates. The result was mixed, in a way that is more disturbing than a simple confirmation or refutation would have been. Some of the photometric candidates were indeed lower redshift interlopers, galaxies at much more modest distances, whose photometric colors had been misinterpreted. But others were spectroscopically confirmed at exactly the extreme redshifts that the photometry had suggested. Real galaxies, genuinely massive and genuinely early, confirmed to be at times when the standard model says such objects should not exist. The JD's survey, in particular, produced spectroscopic confirmations of several galaxies at redshifts above 10, with one object, JADES-GS-Z14-0, confirmed at a redshift of approximately 14.32, corresponding to a time when the universe was approximately 290 million years old. This galaxy has a luminosity and inferred stellar mass that challenges the models at a basic level. For such a massive, luminous galaxy to exist at this epoch, it would have needed to convert gas into stars at extraordinarily high efficiency, essentially converting every available atom of hydrogen into stars as fast as physics allows. The galaxy even shows emission from oxygen, a heavy element that is produced by stars and then ejected when those stars die in supernovae. Oxygen in a galaxy at redshift 14 means that at least one generation of massive stars had already formed, lived, and died before the universe was 300 million years old. The stellar life cycle is compressed almost beyond belief. Astronomers began calling these objects impossibly early galaxies, a phrase that carries the specific technical meaning discussed above. Not literally impossible, but incompatible with the standard hierarchical assembly picture of galaxy formation that Lambda CDM predicts. Chapter 5: The Little Red Dots. A mystery within the mystery. Even as the impossibly early galaxies were generating debate and scrambling the galaxy formation models, Webb revealed another population of bizarre objects that added a new layer of confusion to the picture of the early universe. They were called the Little Red Dots. The name is descriptive and informal, coined by the astronomers who first identified them in the Webb data. The objects were compact, unresolved or barely resolved by Webb's instruments, meaning their physical sizes were very small. And they were red. Their colors, across the wavelength range Webb observes, were dramatically redder than the colors expected for normal star-forming galaxies at any redshift. When the first set of little red dots appeared in the Sears survey data in 2022, astronomers initially assumed they were massive, old, dust-reddened galaxies at high redshift. The redness was attributed to older stellar populations and dust extinction, both of which redden the light from galaxies in ways that are well understood. The compactness was attributed to the high redshift. Small galaxies far away appear compact and unresolved. The masses inferred from the photometry were enormous. Some objects appeared to be among the most massive galaxies known at their epochs, with stellar masses comparable to or exceeding present-day giant elliptical galaxies. If these initial interpretations were correct, the little red dots were yet another population of impossibly early massive galaxies, providing independent evidence of a crisis in the galaxy formation models. But the spectroscopic follow-up told a different story. The spectra of the little red dots revealed something unexpected. Instead of showing the spectral signatures of old, dusty stellar populations, the smooth, declining continuum of an old red galaxy with various absorption features from stellar atmospheres, many of the little red dots showed spectra dominated by broad emission lines. Broad emission lines are the spectroscopic signature of active galactic nuclei, the supermassive black holes at the centers of galaxies that are actively accreting gas and shining as quasars. The light from these objects was not primarily starlight at all. It was the radiation from accretion disks around growing supermassive black holes. This resolved the mystery of the extraordinary redness. The emission lines, which fall in specific wavelength positions in the rest frame UV, were being shifted by the cosmological redshift into the red and near-infrared wavelengths, where Webb observes. The objects were not dusty galaxies. They were a new population of compact, low-luminosity active galactic nuclei at high redshift, what some researchers began calling Little Red AGN. The relief that this provided, the crisis of impossibly massive early galaxies, was perhaps partly resolved by this new interpretation, was quickly replaced by new puzzlement, because the little red dots, even in their AGN interpretation, were deeply strange. Normal AGN, quasars and Seyfert galaxies, show a characteristic spectral signature, a broad emission line profile, where the emission line has broad wings extending far on either side of the line center, reflecting the Doppler broadening from gas moving at thousands of kilometers per second in the vicinity of the black hole. This broad line signature was indeed present in the little red dot spectra. But alongside it, many of the objects showed an unusual feature: a strong Balmer break, a drop in flux at specific wavelengths associated with the absorption of light by hydrogen in stellar atmospheres, that indicated a substantial stellar population surrounding the compact AGN nucleus. The combination of a broad line AGN component and a stellar component in the same compact object was unusual. It suggested that these objects were actively growing supermassive black holes embedded in compact massive host galaxies. An AGN galaxy combination at redshifts and masses where such systems are not expected in the standard models. And then the photometric estimates of the object's properties began to be updated in light of the AGN interpretation. If a significant fraction of the observed light was coming from the AGN rather than from stars, then the stellar mass estimates derived from the photometry, which assumed the light was all from stars, were overestimates. The objects were less massive than the initial photometric estimates suggested. Some of the crisis of impossibly massive early galaxies was resolved, but the nature of the little red dots themselves remained problematic. The number density of these objects, how many of them exist per unit volume of the early universe, significantly exceeds the predictions of models for the AGN population at these redshifts. There are far more compact AGN in the early universe than the models said there should be. And the black hole, masses inferred from the widths of the broad emission lines are often unexpectedly large. Black holes that are too massive for their apparent host galaxy masses, a reversal of the expected relationship between black hole mass and host galaxy properties. The little red dots, in other words, are a mystery within the mystery. They initially appeared to be massive galaxies that galaxies' formation models could not accommodate. They turned out to be something different, something that is also not fully accommodated by the models, just in a different way. The specific discovery that fooled astronomers, finding that what they thought were galaxies were mostly AGN, did not solve the problem. It replaced one problem with another. The early universe, as revealed by Webb, is turning out to be populated by objects that the models did not predict in the right quantities, with the right properties in the right distributions. Not in one category of object, in multiple independent categories. Not with a single systematic bias, with multiple independent signatures of discrepancy. The pattern is not one of a single miscalibration that, once corrected, brings the models back into agreement. It is a pattern of consistent, systematic excess across multiple independent probes, more massive galaxies, more and larger black holes, more structured objects at earlier cosmic epochs than the models predict. Chapter 6: What the rivals are fighting about, and why both sides are partially right. Science is not a placid search for truth conducted in collegial harmony. It is a competitive, adversarial enterprise in which groups of researchers with different methodologies, different theoretical commitments, and different professional stakes compete to establish what is true. The Hubble tension has generated one of the most intense scientific fights in cosmology in decades, with multiple competing groups publishing conflicting results and making competing claims about whose measurements are correct. The most prominent alternative measurement of H0 from the distance ladder comes not from the SH0ES team, led by Rees, but from the competing team of Wendy Friedman at the University of Chicago. Friedman pioneered the use of Cepheid variables for measuring the Hubble constant in the 1990s with the Hubble Key project, which produced one of the first precise measurements of H0. Her team has continued to work on H0 measurements using different calibrators and methods. In 2019, Friedman and collaborators published a measurement using the tip of the red giant branch, TRGB, as a distance indicator, a method that uses the fact that stars of a particular type, low-mass red giant branch stars, reach a precisely determined maximum luminosity at the tip of the red giant branch, providing a standard candle that is independent of Cepheids and potentially free from some of the systematic errors that affect Cepheid-based measurements. Their result? H0 equals 69.8 plus or minus 1.9 kilometers per second per megaparsec. This is intermediate between the SH0ES value of 73 and the Planck value of 67.4. If correct, it would suggest that the tension is less severe than the SH0ES team claims, perhaps consistent with a modest systematic error rather than new physics. Friedman has argued that some of the calibration choices made by the SH0ES team may be inflating their H0 value, and that a more conservative analysis using different calibrators produces a lower value more consistent with the CMB. The SH0ES team has pushed back, arguing that the TRGB method has its own potential systematic errors, specifically in the 0-point calibration of the TRGB luminosity, which is measured primarily in the Large Magellanic Cloud, and may not translate perfectly to the more distant galaxies used in the H0 measurement. They argue that when the TRGB calibration is corrected using geometric distance measurements from Gaia parallaxes, the TRGB-based H0 converges toward their higher value. Webb entered this fight as well. In 2024, Friedman's team published a new measurement using Webb observations and a third type of distance indicator, the J-region asymptotic giant branch, JAGB, stars, which also reach a predictable maximum luminosity. Their result? H0 equals 67.96 plus or minus 1.85 kilometers per second per megaparsec, essentially identical to the Planck CMB value. No tension. This result, if correct, would mean the Hubble tension is an artifact of systematic errors in the Cepheid-based methods, not a signal of new physics. Friedman's team argued that their JAGB method was free from the contamination issues that might affect Cepheid measurements, and that the agreement with the CMB was evidence that the standard cosmological model was correct after all. The response from Rees and the SH0ES team was swift and detailed. In a series of papers, they argued that the Friedman team's JAGB calibration was subject to its own systematic uncertainties. Tools, specifically, that the selection of JAGB stars from the underlying stellar populations in distant galaxies is difficult and may be contaminated by other stellar types that have similar colors but different luminosities. They showed that using different selection criteria for the JAGB stars could shift the inferred distance moduli by amounts sufficient to reconcile the measurement with the higher SH0ES value. This is, on the surface, a highly technical dispute about the photometric selection of specific classes of evolved stars in distant galaxies. But beneath the technical details, it represents a fundamental question about whether the universe contains new physics. There is a third piece of evidence that is worth introducing at this point, because it provides a completely independent handle on the tension and its magnitude: baryon acoustic oscillations, or BAO. Baryon acoustic oscillations are patterns in the large-scale distribution of galaxies, preferred scales in galaxy clustering that are analogous to the acoustic peaks in the CMB. They arise from the same physics: sound waves propagating in the early universe's photon baryon plasma, frozen in at recombination, imprinting a characteristic length scale on the distribution of matter, because the physical length of the BAO scale can be calculated from the early universe physics and compared to the observed angular scale of BAO in galaxy surveys. BAO measurements provide an independent cosmological distance scale. The Dark Energy Spectroscopic Instrument, DESI, released its first-year results in 2024, measuring BAO from a survey of millions of galaxies and quasars. The DESI BAO results, combined with the CMB data, give an H0 that is consistent with the Planck value of approximately 67 to 68. In the DESI results, there is no Hubble tension. The early universe measurements all agree with each other. This creates a striking picture. On one side, the CMB, the BAO surveys, and some alternative distance ladder measurements, all pointing to H0 near 67 to 68. On the other side, the SH0ES Cepheid supernova distance ladder, consistently producing H0 near 73. The tension is between the direct geometric and astrophysical distance measurements in the late universe and the inferences from the early universe physics. The scientific community is genuinely divided. There are excellent researchers who believe that the tension will eventually be resolved by finding and correcting a remaining systematic error in the distance ladder methods. There are equally excellent researchers who believe that the systematic errors have been exhausted and that the tension is pointing toward physics beyond lambda CDM. And there are researchers who maintain that the evidence is currently insufficient to distinguish between these possibilities, that more data is needed, and that premature declarations of new physics are unwarranted. What is not in dispute, what the full weight of evidence from multiple independent methods has established, is that the Hubble tension is real at a statistically significant level, that it has persisted as data quality has improved, and that the simplest explanations have been ruled out. The question is not whether there is a discrepancy. The question is what the discrepancy means. Chapter 7: The Theoretical Landscape. What physics could be missing? If the Hubble tension is real? If the universe truly expands at 73 locally, and 67 inferred from the early universe, and if no measurement error explains the gap, then something in the standard cosmological model must be wrong. The question is what? The standard model, lambda CDM, rests on several foundational assumptions. The universe is described by general relativity. It contains ordinary matter, cold, dark matter, and a cosmological constant, lambda, a constant energy density of empty space that drives accelerating expansion and is identified with dark energy. The initial conditions were set by inflation. a period of exponential expansion in the first fractions of a second that smoothed the universe and seeded the density fluctuations that became galaxies. These assumptions have been tested against enormous amounts of data and have held up with remarkable precision. But they are assumptions. They could be wrong. The theoretical proposals for resolving the Hubble tension fall broadly into two categories. The first modifies the early universe, changing something about the physics that the CMB is sensitive to in a way that shifts the CMB inferred H0 toward the local measurement value. The second modifies the late universe, changing something about the expansion history between recombination and today, in a way that changes the relationship between the CMB conditions and the local expansion rate. The most extensively studied early universe modification is the early dark energy model. In this scenario, there is an additional component of dark energy beyond the cosmological constant that was significant in the early universe around the time of matter radiation equality, and then decayed away afterward. This early dark energy would change the sound horizon at recombination, the length scale imprinted by the acoustic oscillations, in a way that shifts the CMB inferred H0 upward, potentially resolving the tension. Early dark energy models have been the subject of intense theoretical and observational scrutiny. The basic mechanism works. You can construct models where adding early dark energy resolves the Hubble tension. The problem is that these models tend to create new tensions elsewhere. In particular, they worsen what is called the S8 tension, a separate discrepancy between the amplitude of matter clustering on small scales, as measured by galaxy surveys, and as predicted by the CMB-based lambda-c-DM model. Resolving the Hubble tension with early dark energy tends to make the S8 tension worse, and vice versa. Finding a model that resolves both simultaneously is difficult, and no consensus candidate has emerged. A second category of early universe modifications involves new relativistic species, particles that behave like radiation and would change the expansion rate in the early universe in ways that shift the CMB inferred H0. A fourth species of neutrino beyond the three known species, a new type of dark radiation or dark sector particles interacting with the standard model sector, have all been proposed. These scenarios are constrained by precision measurements of the CMB that are sensitive to the total radiation density, and most simple versions of these models are already excluded by current data. On the late universe side, modifications to the expansion history between recombination and today can also in principle resolve the tension. Dark energy that is not a cosmological constant, but evolves with time, what cosmologists call dynamical dark energy, with a time-varying equation of state, can produce a different expansion history that reconciles the early and late measurements. The DESI results mentioned earlier are interesting in this context. Their BAO measurements show a preference for dark energy with a time-varying equation of state at the roughly 2 to 3 sigma level. A hint, not a discovery, but a consistent signal pointing toward dynamical dark energy. If dark energy is evolving, the lambda-CDM model is wrong in a specific testable way. The cosmological constant, the simplest possible form of dark energy, would need to be replaced by a dynamical field, and the properties of that field would need to be constrained by future surveys. This would not necessarily resolve the Hubble tension in its current form, but it would open the door to richer, dark energy physics that might accommodate both the Hubble tension and other anomalies in the cosmological data. There is a more radical possibility that deserves mention, though it is currently considered less likely by most cosmologists. The tension might indicate that general relativity, the theory of gravity that underlies all of cosmology, is wrong or incomplete at cosmological scales. Modified gravity theories have been proposed in various forms, and some of them predict different expansion histories from lambda CDM. The challenge with modified gravity is that general relativity is extraordinarily well tested at solar system scales, neutron star scales, and at the scales probed by gravitational wave astronomy. Getting modified gravity to agree with all of these constraints while also resolving the Hubble tension is extremely difficult. There is also a class of explanations that involves our local environment. Specifically, the possibility that we are in an unusual region of the universe where the local expansion rate differs from the global average. If our local group of galaxies is embedded in a large underdense region, a cosmic void, the local expansion rate could be higher than the global average simply because there is less gravitational braking from surrounding matter. This local void explanation can account for some of the Hubble tension, but detailed analysis of the galaxy distribution around us has not found evidence for a void of the size and depth required to fully explain the tension. The honest summary of the theoretical landscape is this: there is no clear front-runner solution. Every proposal that resolves the Hubble tension creates new tensions elsewhere in the cosmological data. Every modification to the standard model that fits some observations fails to fit others. The universe appears to be presenting cosmologists with a genuinely new situation, a set of interrelated anomalies that resist simple explanation within the current theoretical framework and may require a more fundamental revision of how we think about the cosmos. This is precisely the situation in which, historically, major theoretical breakthroughs occur. The perihelion precession of Mercury, the anomalous rotation of Mercury's orbit that Newtonian gravity could not explain, was a genuine signal that the theory of gravity was incomplete. The resolution was general relativity. The ultraviolet catastrophe, the failure of classical physics to predict the spectrum of blackbody radiation, was a genuine signal that classical mechanics was incomplete. The resolution was quantum mechanics. The pattern in physics has been anomalies that resist simple explanation within the existing framework ultimately point toward the existence of a deeper framework. The Hubble tension may be that kind of signal, or it may turn out to be a systematic error that current techniques cannot identify. The history of science also contains many examples of anomalies that looked profound and turned out to be measurement artifacts. The difference in the current case is that the anomalies are multiple and independent. The Hubble tension, the impossibly early galaxies, the little red dots, the possible hints of dynamical dark energy from DESI, these are not the same measurement from different angles. They are different measurements of different phenomena using different techniques, and they all point in the same direction, toward a universe that is more complex, more structured, and more active at early times than the standard model predicts. When independent lines of evidence converge on the same conclusion, that is precisely the situation in which science updates its fundamental models. Chapter 8: The S8 tension. The second crack in the foundation. The Hubble tension is not the only number in cosmology that refuses to behave. There is a second, quieter crisis running in parallel. Less famous than the Hubble tension, less visible in the popular science press, but equally troubling to the researchers who study it. It is called the S8 tension, named after a specific parameter that describes the clumpiness of matter in the universe, and it adds a second independent line of evidence to the case that the standard cosmological model is incomplete. To understand the S8 tension, you need to understand what S8 actually measures. The universe is not uniformly smooth. Matter is clumped. Galaxies cluster in groups and clusters, and superclusters, separated by vast empty voids. The degree of this clumpiness on large scales is predicted by the Standard Model from the initial density fluctuations imprinted in the early universe, grown under the influence of gravity over 13.8 billion years. S8 is essentially a combined measure of two things: the overall density of matter in the universe and the amplitude of matter density fluctuations on scales of roughly 8 megaparsecs. Lambda CDM makes a specific quantitative prediction for S8. The CMB, which encodes the early universe's initial conditions, combined with the Standard Model's description of how those conditions evolved, predicts a specific value of S8 for the present-day universe. That predicted value is approximately 0.83. But when astronomers measure S8 directly in the late universe, by mapping the distribution of galaxies and using the statistics of gravitational lensing to infer how matter is distributed along lines of sight, they get a consistently lower value. Weak gravitational lensing surveys, which measure the tiny distortions in the shapes of background galaxies produced by the gravitational influence of foreground matter, have found S8 values in the range of 0.74 to 0.78. The KIDS survey, the DES survey, the HSC survey. Different instruments, different areas of sky, different analysis methods, all finding less clustering than the Standard Model predicts. The discrepancy is smaller in statistical significance than the Hubble tension, typically 2 to 3 sigma rather than 5, and individual measurements carry larger uncertainties. But the systematic direction of the discrepancy is consistent. The universe, as measured by weak lensing in the late epoch, appears to be less clumpy than the CMB-based Lambda CDM model says it should be. There is a specific and important way that the S8 tension interacts with the Hubble tension that makes the combination particularly troubling for theorists. As noted in the previous chapter, the most studied family of solutions to the Hubble tension, early dark energy models, resolves the Hubble tension by adding an additional energy component to the early universe that changes the sound horizon scale and shifts the CMB inferred H0 upward toward the local measurement. But these same early dark energy models, when applied to the S8 parameter, tend to predict more matter clustering rather than less. They make the S8 tension worse rather than better. This creates what physicists sometimes call a cosmological whack-a-mole situation. You press down one anomaly with a model modification, and another anomaly pops up somewhere else. The theoretical community has been searching for years for a single modification to Lambda CDM that simultaneously resolves both the Hubble tension and the S8 tension without creating new discrepancies elsewhere. No such model has achieved consensus. Several candidates have been proposed, but each one faces objections. The DESI first-year results added a new dimension to this picture. In addition to the BAO measurements that were headline news, the DESI team found hints in their data at the level of 2 to 3 sigma, consistent with the type of signal that warrants attention, but not yet declaration. That the dark energy equation of state has evolved over cosmic time. Dark energy in the early universe may have behaved differently from dark energy today. The equation of state parameter, conventionally labeled W, appears from the DESI data to have been less than -1 in the distant past and to be evolving toward -1 today. A pattern called phantom crossing that is not predicted by the simplest dark energy models. If dark energy is truly dynamical, if its properties evolve with cosmic time rather than being fixed at the cosmological constant value, then the entire history of the universe's expansion is different from what lambda CDM assumes. The relationship between the early universe conditions imprinted in the CMB and the late universe expansion rate measured by the distance ladder would be modified in ways that could, in principle, simultaneously address the Hubble tension and other anomalies. But the specific form of the dynamical dark energy required to do this coherently is not yet established. There is something more philosophically significant about the combination of the Hubble tension and the S8 tension than either one individually. Both tensions are between early universe and late universe measurements. In both cases, the early universe, as encoded in the CMB, predicts something that the late universe, measured directly, does not deliver. The universe is expanding faster than expected locally, Hubble tension. The universe is clumping less than expected locally, S8 tension. These two facts, taken together, paint a picture of a late universe that is simultaneously expanding faster and clustering less than the early universe conditions predict. A universe that is, in some sense, more diffuse and more spread out than the standard model expected. This is not an incoherent picture. A universe that is expanding faster would naturally also tend to be less clumped because the faster expansion would more efficiently disperse structures. But in the specific quantitative context of lambda CDM, the two tensions do not naturally arise from the same single modification. This suggests that whatever is missing from the standard model is not a small correction that leaves the rest of the framework intact. It is a modification that touches the expansion history, the clustering dynamics, and possibly the nature of dark energy or dark matter in ways that the current theoretical framework does not accommodate. The S8 tension is, in this sense, not a second crisis, but the second dimension of the same crisis. Together with the Hubble tension, the impossible early galaxies, and the DESI hints of dynamical dark energy, it forms a coherent portrait of a universe that is not behaving as the standard model predicts in a consistent and directional way across multiple independent observational probes. Chapter 9. What history tells us about moments like this? The situation in cosmology right now. Multiple independent anomalies that resist resolution within the existing theoretical framework, pointing consistently in the same direction away from the standard model, has historical precedents. And those precedents are informative in a way that is both exciting and humbling. the most instructive parallel is the situation in physics at the turn of the 20th century. Classical physics, Newtonian mechanics, and Maxwell's electromagnetism was, by any reasonable assessment, one of the most successful theoretical frameworks in the history of human thought. It had been tested to extraordinary precision in every accessible domain. It predicted the motions of the planets, the behavior of electrical circuits, the propagation of light, the properties of heat and sound. There was a widespread feeling in the 1890s that physics was essentially complete, that the task remaining was not to discover new principles, but to measure known ones more precisely. And then the anomalies arrived, not singly, but in a cluster. The Michelson-Morley experiment showed that the speed of light was the same in every direction, regardless of the Earth's motion through space. A result that was incompatible with the prevailing picture of light propagating through a medium called the ether. The photoelectric effect showed that light behaved as if it were composed of discrete packets of energy rather than continuous waves, contradicting Maxwell's electromagnetic theory. The spectrum of black-body radiation, the distribution of light emitted by a hot object, could not be reproduced by classical statistical mechanics. The calculation gave a prediction called the ultraviolet catastrophe that diverged to infinity at short wavelengths, an obvious impossibility. The orbit of Mercury refused to precess at exactly the rate Newtonian gravity predicted. The discrepancy was small, but precisely measured and stubbornly real. Each of these anomalies, individually, might have been dismissed as a measurement error or a temporary puzzle, waiting for a clever explanation within the existing framework. Together, they pointed to something more fundamental. The resolution, in the 2 decades from roughly 1900 to 1920, was the twin revolutions of quantum mechanics and general relativity. 2 theoretical frameworks so different from classical physics that they were not merely corrections to the existing picture, but replacements of its foundations. Quantum mechanics replaced the classical picture of particles and waves with a framework in which the distinction dissolves, in which measurement fundamentally alters what is measured, in which probability is not a computational convenience, but a fundamental feature of nature. General relativity replaced Newton's absolute space and time with curved space-time, replaced gravitational force with the geometry of space-time, and described a universe that was not the fixed background stage of Newtonian mechanics, but an active, dynamic participant in the physics of matter and energy. These were not incremental improvements. They were paradigm shifts. To use the language of the philosopher Thomas Kuhn, who studied exactly this kind of revolutionary episode in the history of science, Kuhn described a pattern in which science proceeds through long periods of normal science, working within an accepted framework, solving puzzles within it, extending its reach, punctuated by episodes of crisis when anomalies accumulate that the framework cannot absorb, followed by a revolution in which the framework is replaced by a new one that accommodates both the new anomalies and everything the old framework got right. The pattern in cosmology today bears a structural resemblance to the early 20th century situation, at least in outline. A highly successful framework, lambda CDM, tested to extraordinary precision in many domains, facing a cluster of anomalies that resist explanation within it, with the specific character of the anomalies suggesting that the required modification is not small. There is an important disanalogy that honest science requires acknowledging. The anomalies in early 20th century physics were, in retrospect, genuinely devastating for classical physics. There was no way to patch them within the existing framework without invoking ad hoc assumptions of rapidly diminishing plausibility. The cosmological anomalies today are real and significant, but the situation is not yet at the same level of clarity. There are still serious researchers who believe the Hubble tension will be resolved by finding a remaining systematic error. The S8 tension is at lower statistical significance than the Hubble tension. The DESI hints of dynamical dark energy are not yet a confirmed discovery. The impossibly early galaxies, while real, are not yet fully characterized in the theoretical models. The historical parallel is suggestive but not conclusive. It tells us what kind of situation could be unfolding, not that this situation is definitely that kind. But there is a second historical parallel that is worth considering, one that is closer in time and closer in the specific domain of cosmology. In 1998, two teams, the SH0ES team's precursor, led by Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, independently published evidence that the universe's expansion was accelerating. The evidence came from Type 1a supernovae appearing dimmer than expected at high redshift, indicating that they were farther away than a decelerating or even constant rate expanding universe would place them. The acceleration implied a new component of the universe's energy budget, dark energy, the cosmological constant, that was not present in the models of the time. The reaction from the cosmological community in 1998 was not uniformly enthusiastic. Many researchers were skeptical. The possibility of systematic errors in the supernova measurements, unknown evolution of Type 1, A supernova properties with redshift, dust absorption effects, selection biases, was serious and taken seriously. The finding went against theoretical prejudices. Most cosmologists in the 1990s expected the universe's expansion to be decelerating due to gravitational attraction between matter. The cosmological constant had been introduced by Einstein and later discarded, and its reintroduction felt inelegant to many. And yet within a few years, independent lines of evidence converged to confirm the acceleration. The CMB, the galaxy clustering statistics, the baryon acoustic oscillations, all consistent with a universe dominated by dark energy. The Nobel Prize in 2011 was the formal recognition that the community had accepted, with high confidence, that dark energy was real and that the universe was accelerating. The point of this parallel is not that the current anomalies will necessarily be resolved by a single dramatic discovery comparable to dark energy's detection. It is that the cosmological community has been in this situation before, facing anomalies in precision measurements that resisted conventional explanation, and that the resolution was not a measurement correction, but a genuine expansion of the physical picture of the universe. Adam Rees was one of the people who found that the universe was accelerating. He is now one of the people who is saying that the measurements of the universe's expansion rate are telling us something we do not yet understand. His track record gives his current assessment specific weight, not because scientists should be deferential to authority, but because this specific person, with this specific history has been right before about exactly this kind of situation. The pattern that history suggests is this: when the best measurements consistently disagree with the best models, when multiple independent methods converge on the same discrepancy, when theoretical explanations consistently fail to resolve the tension without creating new problems, and when the person who knows the measurements best says the systematic errors have been exhausted. These are the conditions under which science has historically been on the verge of genuine discovery. Not every anomaly is a discovery in waiting, but the current cluster of anomalies in cosmology has the structural hallmarks of the kind that are. Chapter 10: Where the Science Actually Stands. Let us be honest about what we know, what we suspect, and what we do not know. The Hubble tension is real. The gap between the distance ladder, H0 measurement of approximately 73, and the CMB inferred H0 of approximately 67.4 has been tested extensively, and the most specific proposed systematic errors have been ruled out by Webb. The tension persists at approximately 5 sigma across multiple independent implementations of the distance ladder. The probability of this level of discrepancy arising from random measurement error, given the claimed uncertainties, is less than 1 in a million. That last sentence requires an important qualification. Probabilities like 1 in a million assume that the stated measurement uncertainties are correct. In practice, the stated uncertainties in complex astrophysical measurements often turn out to underestimate the true error, either because systematic errors are not fully captured, or because the statistical analysis makes assumptions that are not perfectly valid. The history of precision measurements is full of cases where 5 sigma discrepancies resolved themselves as measurement practice improved. The Hubble tension may still be in this category, but the weight of evidence is shifting against this interpretation. Wendy Friedman's team, using completely independent calibrators, gets a value intermediate between 67 and 73, closer to 68 in their most recent Webb analysis. The SH0ES team argues that this result has its own systematic issues. The debate between these two groups is genuine, technical, and unresolved. But neither group's measurement is compatible with a Hubble constant significantly below 68. The region below 68, where the CMB model naturally points, is not where any careful distance ladder measurement currently lands. This asymmetry is telling. If the tension were due to systematic errors in the distance ladder, we would expect the different distance ladder methods to give a range of values scattered on both sides of the CMB value, with some measurements high and some low. Instead, all the careful distance ladder measurements are above the CMB value. The spread is around 68 to 73, not 62 to 78. The measurements are not randomly distributed around the CMB value with a positive bias. They are consistently above it, regardless of the specific calibrator used. That pattern is more consistent with the CMB value being low than with the distance ladder values being randomly biased high. For the CMB value to be low, for the Planck analysis to be systematically underestimating H0, something in the early universe physics used to infer H0 from the CMB would need to be wrong. This is the realm of new physics, early dark energy, new light particles, modified early universe dynamics. these are not impossible. They are being taken seriously by theorists. But they have not produced a consensus solution, and they tend to create new problems when they are implemented. The early galaxy findings from Webb are more uncertain in their interpretation. The spectroscopically confirmed impossibly massive early galaxies are real. JADES-GS-Z 14-0 and its siblings cannot be explained away as misidentified lower redshift objects. But the degree to which they challenge the standard model depends on how the stellar mass-to-light ratio is calibrated for these objects. And that calibration carries uncertainties that are difficult to fully constrain with available data. Some researchers argue that the apparent tension with the models can be resolved by invoking more efficient early star formation. Star formation happening at rates closer to the theoretical maximum than the models assume. Others argue that even the maximum star formation efficiency is insufficient to produce what Webb is finding. The distinction between the models are incomplete in their treatment of star formation physics, and the underlying cosmological framework needs modification is not yet clearly resolved by the early galaxy data. The galaxy formation models built on top of lambda CDM have enough free parameters that, in principle, they can be adjusted to accommodate more efficient early star formation without modifying the cosmological model itself. Whether the required adjustments are physically plausible is debated. Whether they are sufficient to fully accommodate the most extreme observations is not yet established. The little red dots have complicated the picture in ways that are still being worked through. The discovery that many of them are AGN rather than stellar mass-dominated galaxies relieved some of the pressure on the models. The most extreme photometric mass estimates were largely explained as misidentification of the dominant emission mechanism. But the residual problems, the excess number density of compact AGN, the overmassive black holes relative to their host galaxies, remain genuine puzzles. They suggest that supermassive black holes grew faster in the early universe than the models predict, which is itself a challenge, though a different kind of challenge from the galaxy mass problem. The DESI hints of dynamical dark energy are intriguing but premature to take as established. The 2 to 3 sigma preference for evolving dark energy from the first year of DESI data is interesting, precisely because it is consistent with the direction that multiple other lines of evidence point toward a universe with richer dark energy physics than the cosmological constant. But 2 to 3 sigma hints have a substantial history of fading away as datasets grow. The DESI collaboration itself has been appropriately cautious in how they present the result, describing it as a hint that warrants further investigation rather than a discovery. The picture that emerges, holding all of this simultaneously, is of a cosmological model under significant but not catastrophic stress. Lambda CDM is not broken in the sense of making predictions that are flatly wrong about most observations. The CMB power spectrum, the large-scale structure of the universe, the light element abundances from Big Bang nucleosynthesis, the history of cosmic acceleration. All of these are well described by the standard model. But in several specific domains, the model is producing predictions that systematically disagree with careful observations. The Hubble tension, the S8 tension, the early galaxy excess, the early black hole excess, the hints of dynamical dark energy. The word systematically is important. These discrepancies are not random. They are directional. They all point toward a universe that was more structured and more active at early times than lambda CDM predicts, and that has been expanding more rapidly in the late universe than the early universe conditions imply. A single model modification that produces more early structure and a higher late universe expansion rate would be a natural candidate for the resolution. No such modification has yet achieved consensus, but the directional consistency of the anomalies is a significant scientific signal. What does Adam Rees actually think? Not in the public statement sense, but in the sense of his working scientific judgment about where things stand? In various interviews and public discussions since the Webb Cepheid results were published, Rees has been remarkably candid. He has said that the possibility of a remaining systematic error cannot be completely ruled out. No scientist should make such a claim, but that the specific systematic errors proposed by critics have been addressed and excluded. He has said that the tension is at a level where, in other areas of physics, the community would be seriously entertaining new physics. He has said that the early universe data from Webb is providing additional lines of evidence that compound the picture of a model under stress. And he has used the specific phrase that this video began with, that we may have misunderstood the universe. That phrase, from that person, in that context, is not a casual remark. It is a carefully calibrated statement from someone who has spent 3 decades measuring the universe's expansion, who won the Nobel Prize for finding that the universe was accelerating in a way the models did not predict, and who is now saying that his measurements are again pointing toward something the models do not predict. The appropriate response to this scientific situation is not panic, and it is not dismissal. It is the response that science always makes to anomalies that are real, robust, and persistent. Engagement. The theoretical community is working. The observational community is planning. New surveys, the Euclid satellite, the Vera Rubin Observatory's Legacy Survey of Space and Time, the Roman Space Telescope, will provide data on galaxy clustering, weak lensing, and the large-scale structure of the universe with statistics orders of magnitude beyond current surveys. New precision distance ladder. Measurements will continue to test and retest the Cepheid calibration with every new tool that becomes available. The DESI survey will eventually produce a dataset large enough to definitively test whether dark energy is constant or dynamical. The answer is coming. It will come from data, as it always does in science. And when it comes, it will be one of 3 things: a measurement correction that resolves the tension without requiring new physics, a model modification within the broad lambda CDM framework that accommodates all the anomalies simultaneously, or something more fundamental, a revision of the foundations of cosmology comparable to the revisions that followed the anomalies of the early 20th century. The weight of evidence right now does not conclusively point to any of these 3 options over the others. That uncertainty is not a failure of science. It is science operating in its natural state, accumulating evidence, testing models, identifying anomalies, working methodically toward understanding. What is clear is that the universe is more interesting and more surprising than the best models predicted. That is always how it has been, at every frontier of human knowledge. And the appropriate response to it is exactly what Rees and his colleagues are doing: measuring more carefully, thinking more rigorously, and following the data wherever it leads. If the Hubble tension is real, if the universe truly expands at 73 locally and 67 inferred from the early universe, and if no measurement error explains the gap, then something in the standard cosmological model must be wrong. The question is what? The standard model, lambda CDM, rests on several foundational assumptions. The universe is described by general relativity. It contains ordinary matter, cold, dark matter, and a cosmological constant, lambda, a constant energy density of empty space that drives accelerating expansion and is identified with dark energy. The initial conditions were set by inflation, a period of exponential expansion in the first fractions of a second that smoothed the universe and seeded the density fluctuations that became galaxies. These assumptions have been tested against enormous amounts of data and have held up with remarkable precision. But they are assumptions. They could be wrong. The theoretical proposals for resolving the Hubble tension fall broadly into two categories. The first modifies the early universe, changing something about the physics that the CMB is sensitive to, in a way that shifts the CMB inferred H0 toward the local measurement value. The second modifies the late universe, changing something about the expansion history between recombination and today, in a way that changes the relationship between the CMB conditions and the local expansion rate. The most extensively studied early universe modification is the early dark energy model. In this scenario, there is an additional component of dark energy beyond the cosmological constant that was significant in the early universe, around the time of matter-radiation equality, and then decayed away afterward. This early dark energy would change the sound horizon at recombination, the length scale imprinted by the acoustic oscillations, in a way that shifts the CMB inferred H0 upward, potentially resolving the tension. Early dark energy models have been the subject of intense theoretical and observational scrutiny. The basic mechanism works. You can construct models where adding early dark energy resolves the Hubble tension. The problem is that these models tend to create new tensions elsewhere. In particular, they worsen what is called the S8 tension, a separate discrepancy between the amplitude of matter clustering on small scales, as measured by galaxy surveys, and as predicted by the CMB-based lambda CDM model. Resolving the Hubble tension with early dark energy tends to make the S8 tension worse, and vice versa. Finding a model that resolves both simultaneously is difficult, and no consensus candidate has emerged. A second category of early universe modifications involves new relativistic species, particles that behave like radiation and would change the expansion rate in the early universe in ways that shift the CMB inferred H0. A fourth species of neutrino, beyond the three known species, a new type of dark radiation, or dark sector particles interacting with the standard model sector, have all been proposed. These scenarios are constrained by precision measurements of the CMB that are sensitive to the total radiation density. And most simple versions of these models are already excluded by current data. On the late universe side, modifications to the expansion history between recombination and today can also, in principle, resolve the tension. Dark energy that is not a cosmological constant, but evolves with time. What cosmologists call dynamical dark energy, with a time-varying equation of state, can produce a different expansion history that reconciles the early and late measurements. The DESI results mentioned earlier are interesting in this context. Their BAO measurements show a preference for dark energy with a time-varying equation of state at the roughly 2 to 3 sigma level. A hint, not a discovery, but a consistent signal pointing toward dynamical dark energy. If dark energy is evolving, the lambda CDM model is wrong in a specific testable way. The cosmological constant, the simplest possible form of dark energy, would need to be replaced by a dynamical field, and the properties of that field would need to be constrained by future surveys. This would not necessarily resolve the Hubble tension in its current form, but it would open the door to richer dark energy physics that might accommodate both the Hubble tension and other anomalies in the cosmological data. There is a more radical possibility that deserves mention, though it is currently considered less likely by most cosmologists. The tension might indicate that general relativity, the theory of gravity that underlies all of cosmology, is wrong or incomplete at cosmological scales. Modified gravity theories have been proposed in various forms, and some of them predict different expansion histories from lambda CDM. The challenge with modified gravity is that general relativity is extraordinarily well tested at solar system scales, neutron star scales, and at the scales probed by gravitational wave astronomy. Getting modified gravity to agree with all of these constraints while also resolving the Hubble tension is extremely difficult. There is also a class of explanations that involves our local environment. Specifically, the possibility that we are in an unusual region of the universe where the local expansion rate differs from the global average. If our local group of galaxies is embedded in a large underdense region, a cosmic void, the local expansion rate could be higher than the global average, simply because there is less gravitational braking from surrounding matter. This local void explanation can account for some of the Hubble tension, but detailed analysis of the galaxy distribution around us has not found evidence for a void of the size and depth required to fully explain the tension. The honest summary of the theoretical landscape is this: there is no clear front-runner solution. Every proposal that resolves the Hubble tension creates new tensions elsewhere in the cosmological data. Every modification to the standard model that fits some observations fails to fit others. The universe appears to be presenting cosmologists with a genuinely new situation, a set of interrelated anomalies that resist simple explanation within the current theoretical framework, and may require a more fundamental revision of how we think about the cosmos. This is precisely the situation in which, historically, major theoretical breakthroughs occur. The perihelion precession of Mercury, the anomalous rotation of Mercury's orbit that Newtonian gravity could not explain, was a genuine signal that the theory of gravity was incomplete. The resolution was general relativity. The ultraviolet catastrophe, the failure of classical physics to predict the spectrum of black-body radiation, was a genuine signal that classical mechanics was incomplete. The resolution was quantum mechanics. The pattern in physics has been anomalies that resist simple explanation within the existing framework, ultimately point toward the existence of a deeper framework. The Hubble tension may be that kind of signal, or it may turn out to be a systematic error that current techniques cannot identify. The history of science also contains many examples of anomalies that looked profound and turned out to be measurement artifacts. The difference in the current case is that the anomalies are multiple and independent. The Hubble tension, the impossibly early galaxies, the little red dots, the possible hints of dynamical dark energy from DESI. These are not the same measurement from different angles. They are different measurements of different phenomena using different techniques, and they all point in the same direction, toward a universe that is more complex, more structured, and more active at early times than the standard model predicts. When independent lines of evidence converge on the same conclusion, that is precisely the situation in which science updates its fundamental models. Conclusion. Let us come back to Adam Rees. He is sitting in his office at Johns Hopkins University or at the Space Telescope Science Institute, surrounded by decades of data. Light curves of Cepheid variables in dozens of galaxies, the calibration notebooks of a career spent building the most precise ruler in cosmology. On his shelves, somewhere, is the Nobel Prize certificate. In his publication list are the papers from 1998 that changed our understanding of what the universe is doing. And he is looking at a number. The number is 73. It has been 73 for years, measured every way he and his team know how to measure it, tested with every systematic correction they can devise, now confirmed by the most powerful telescope ever built. The number is 73, and on the other side of his desk or on the screen is the other number. The number is 67. It comes from the Planck satellite, from the pattern of fluctuations in the oldest light in the universe, from a completely independent method that probes completely different physics. The number is 67. The gap between these two numbers, 6 units, 8%, 5 standard deviations, is the gap that the Nobel Prize winner is saying may mean we have misunderstood the universe. Not slightly misunderstood, in the way that all scientific models are imperfect approximations, but fundamentally misunderstood in the way that Newtonian physics was fundamentally misunderstood about gravity, in the way that classical physics was fundamentally misunderstood about the behavior of light and matter. It is worth being precise about what that claim means and what it does not mean. It does not mean the Big Bang did not happen. The evidence for the Big Bang, the CMB, the abundances of light elements from Big Bang, nucleosynthesis, the age of the oldest stars, the observed expansion of the universe, is overwhelming and is not challenged by the Hubble tension. Whatever is missing from the standard model is missing from a layer of physics built on top of the confirmed Big Bang foundation. It does not mean the universe is not expanding. That has been known since Hubble in 1929 and is measured independently in dozens of ways. The tension is not about whether expansion is happening, but about how fast. It does not mean dark energy does not exist. The accelerating expansion of the universe, the discovery for which Rees won his Nobel Prize, is one of the best established facts in modern cosmology. What it might mean is that dark energy is more complex and more interesting than the simplest possible form, the cosmological constant that the standard model assumes. What it might mean is that the universe contains physics we do not yet know about. physics that operates in the early universe and changes the conditions from which the CMB emerged. Physics that affects the expansion history in ways that create a difference between what the early universe conditions predict for the current expansion rate and what the current expansion rate actually is. Physics that also affects how galaxies assembled in the first billion years, how black holes grew, how matter clustered, how dark energy behaves across cosmic time. Physics that is real, physical, and discoverable. Not magic, not a failure of science, but a gap in our knowledge waiting to be filled by the same process that has filled every previous gap. Careful observation, rigorous analysis, creative theoretical thinking, and the patient accumulation of evidence. There is something that the popular coverage of cosmological anomalies gets wrong, and it is worth correcting explicitly. The fact that the standard model is under stress is not evidence that science is in crisis. It is evidence that science is working. The standard model of cosmology, lambda CDM, is a scientific theory, which means it makes testable predictions that can be confirmed or refuted by measurement. The fact that some of those predictions are now being refuted by increasingly precise measurements is not a failure of the framework. It is the framework doing exactly what scientific frameworks are supposed to do, making precise predictions that allow nature to tell us when we have gotten something wrong. When Newtonian physics was found to predict the wrong precession rate for Mercury's orbit, that was not evidence that Newtonian physics was useless or that scientists had failed. It was evidence that a better theory of gravity existed and was waiting to be discovered. General relativity was that theory. When lambda CDM is found to predict the wrong Hubble constant and the wrong early galaxy abundances, that is not evidence that cosmology is in crisis. It is evidence that a better cosmological model exists and is waiting to be discovered. The question is what that model will look like. And here is where the situation becomes genuinely exciting, rather than merely alarming. The specific character of the anomalies, the direction they point, the domains they affect, the interrelated way they compound each other, is information. It is not random noise. It is a signal about the nature of the new physics required. The theoretical community is using that signal to constrain the space of possible models, testing each proposed modification against all available data and identifying the models that survive. The observational community is planning measurements with Euclid, with Rubin, with Roman, with DESW's continuing expansion, with the next generation of CMB experiments that will generate the data needed to test the survivors. The physicist Richard Feynman once described the scientific process in terms that are applicable here. He said that if a theory disagrees with experiment, then the theory is wrong. Not almost wrong, not wrong in an unimportant domain, not wrong in a way that can be corrected by an incremental adjustment. Wrong. And the right response is not to protect the theory, but to find a better one. Adam Riess's measurements disagree with the model. The impossibly early galaxies disagree with the model. The S8 tension disagrees with the model. The DESI hints of dynamical dark energy disagree with the simplest version of the model. The model may be wrong in some specific and ultimately discoverable way. And that is not a reason for despair. It is a reason for excitement. The universe is holding back a secret. The measurements are increasingly precise, and the anomalies are increasingly robust. The secret is being narrowed down, constrained, identified in outline, if not yet in detail. We may be living through the early stages of the next revolution in our understanding of the cosmos, the one that comes after lambda CDM, the one that accommodates everything. Lambda CDM got right. The Big Bang, the dark matter, the large-scale structure, the accelerating expansion, while adding whatever ingredient is producing the measured Hubble constant of 73, the excess of early massive galaxies, the lower-than-expected matter clustering, and the hints of evolving dark energy. That ingredient has not yet been identified. The theory has not yet been written. But the data that will constrain it is being collected right now by James Webb and Euclid and DESI and Planck's successors in a global scientific enterprise of extraordinary precision and ambition. Adam Rees says we may have misunderstood the universe. He is probably right. And the history of science says that this kind of misunderstanding, when it is found and corrected, leads to the deepest and most profound advances in human knowledge. The universe is not broken. Our model of it is incomplete. And that is exactly the kind of problem that science knows how to solve.